When the James Webb Space Telescope launched on Christmas Day 2021, astronomers around the world held their breath. This wasn't just another telescope. It was a time machine designed to peer deeper into the cosmic past than any instrument before it. And when those first images arrived in July 2022, they didn't disappoint. But what James Webb actually revealed about the early universe is far more fascinating than any clickbait headline could capture. Today, we're going to explore the real discoveries, the genuine mysteries, and what they mean for our understanding of cosmic history. Section 1. The Deep Field Revelation. Let's start with that first deep field image. You've probably seen it. Thousands of galaxies, each containing billions of stars, filling a patch of sky smaller than a grain of sand held at arm's length. But here's what made astronomers sit up and take notice. Some of those galaxies were shining just 300 to 400 million years after the Big Bang. To put that in perspective, the universe is 13.8 billion years old. These galaxies formed when the universe was barely 2 to 3% of its current age. Now, we expected to find early galaxies. That was the whole point of building James Webb. What we didn't expect was how many there were and how bright they appeared. Previous models, based on observations from Hubble and other telescopes, suggested that galaxies in this era should be relatively small, dim, and rare. But James Webb found them in abundance. In just the first few months of observations, the telescope identified dozens of galaxy candidates from this early epoch. Some of these galaxies appear surprisingly mature. They show signs of organized structure, spiral arms, bars, even central bulges, features that theoretically should take much longer to develop. One galaxy, dubbed Glass Z13, appeared to form just 300 million years after the Big Bang. Its light has been traveling for over 13 billion years to reach us. When we look at this galaxy, we're seeing it as it was when the universe itself was an infant. But here's the critical question astronomers are now asking. How did these galaxies assemble so quickly? Section 2. The Assembly Problem. To understand why early galaxies are puzzling, we need to understand how galaxies form. In the standard model of cosmology, galaxies grow gradually. First, tiny fluctuations in the early universe, quantum ripples stretched to cosmic scales by inflation, create regions slightly denser than their surroundings. Dark matter, which doesn't interact with light, begins to collapse into these regions first, forming gravitational wells. Normal matter, the stuff stars and planets are made of, falls into these dark matter wells. Over millions of years, gas clouds collide, fragment, and ignite to form the first stars. These stars cluster together, forming small proto-galaxies. These proto-galaxies then merge, slowly building up into the grand spiral and elliptical galaxies we see today. This process is called hierarchical assembly, and it should take time, hundreds of millions to billions of years. But James Webb is showing us galaxies that appear to assemble remarkably fast. Some contain billions of solar masses worth of stars, all formed in just a few 100 million years. How is this possible? One possibility is that star formation in the early universe was simply more efficient than we thought. Perhaps the conditions back then, denser gas, different chemical compositions, more frequent galaxy interactions, allowed stars to form much more rapidly. Another possibility involves supermassive black holes. James Webb has discovered black holes with masses millions of times that of our Sun, existing when the universe was less than 1 billion years old. These black holes might have helped regulate star formation, or they might have formed through processes we don't yet fully understand. There's also a third, more radical possibility. Our models of galaxy formation might need fundamental revision. This doesn't mean the Big Bang is wrong or that cosmology is broken. It means we're refining our understanding, filling in details we couldn't observe before. Science advances by finding discrepancies between predictions and observations. James Webb is giving us those discrepancies, and that's exactly what we need to improve our theories. Section 3. The First Stars and Cosmic Dawn. One of James Webb's primary missions was to observe the cosmic dawn, the period when the first stars ignited and began transforming the universe. Before stars existed, the universe was a dark place. After the Big Bang and the brief period of recombination, the cosmos was filled with neutral hydrogen gas. This gas absorbed most wavelengths of light, making the universe opaque. Scientists call this the cosmic dark ages. Then, somewhere between 100 and 400 million years after the Big Bang, the first stars formed. These weren't stars like our sun. They were massive, perhaps 100 or even 1,000 times more massive, and incredibly hot. They burned through their fuel in just a few million years, then exploded as supernovae. But in their brief lives, these stars did something crucial. They re-ionized the universe. Their intense ultraviolet radiation split hydrogen atoms back into protons and electrons, making space transparent to light once again. James Webb has been searching for signatures of this reionization process, and it's found evidence in the spectra of distant galaxies. By analyzing the light from these galaxies, astronomers can see how much of the surrounding hydrogen is neutral versus ionized. This tells us when and how reionization occurred. What's emerging is a picture of reionization as a patchy, gradual process. It didn't happen all at once across the universe. Instead, bubbles of ionized hydrogen formed around the first galaxies, then slowly expanded and merged over hundreds of millions of years. James Webb has also been hunting for population 3 stars, the theorized first generation of stars, made purely from hydrogen and helium with no heavy elements. These stars should have distinct spectral signatures. So far, we haven't confirmed a population 3 star, but James Webb has found extremely metal-poor galaxies, containing stars with very low abundances of elements heavier than helium. These might be among the earliest stellar populations, formed just after the first generation. The search continues, and every observation brings us closer to understanding how the universe lit up for the first time. Section 4. Chemical Evolution and Early Enrichment. Here's something that surprised many astronomers. James Webb found heavy elements in very early galaxies. After the Big Bang, the universe contained only the lightest elements, hydrogen, helium, and trace amounts of lithium. Everything heavier, carbon, nitrogen, oxygen, iron, gold, was created inside stars. When massive stars explode as supernovae, they scatter these heavy elements into space. Over successive generations of stars, the universe becomes progressively enriched with heavier elements. We expected early galaxies to be chemically primitive, containing mostly hydrogen and helium. But James Webb spectroscopy reveals that some galaxies, barely 500 million years old, already contain significant amounts of oxygen, carbon, and other heavy elements. This means that not only did stars form quickly, but they also lived, died, and enriched their environments remarkably fast. Multiple generations of stars must have cycled through their lifespans in just a few 100 million years. One particular galaxy, observed when the universe was about 700 million years old, shows oxygen levels about 1/5 that of our sun. That might not sound like much, but it represents substantial chemical enrichment in a very young universe. This rapid enrichment has implications for the formation of planets and potentially life. Heavy elements are necessary for rocky planets like Earth. If these elements appeared early, then potentially habitable planets could have formed much earlier in cosmic history than previously thought.
Section 5. Supermassive black holes in infant galaxies. Perhaps one of James Webb's most intriguing discoveries involves supermassive black holes in the early universe. We've known for decades that most large galaxies, including our own Milky Way, harbor supermassive black holes at their centers. These monsters can contain millions or even billions of times the mass of our sun. The relationship between galaxies and their central black holes is intimate. The mass of the black hole correlates with properties of the galaxy's central bulge. Somehow, the growth of the black hole and the galaxy are connected. But how do supermassive black holes form? This is one of the outstanding questions in astrophysics. The standard model suggests they start from stellar mass black holes, the remnants of massive stars, and grow over time by accreting matter and merging with other black holes. But this process is slow. It should take billions of years to build up supermassive black holes. James Webb has now observed quasars, extremely bright objects powered by actively feeding supermassive black holes from when the universe was less than 1 billion years old. Some of these black holes have masses approaching 1 billion solar masses. How did they get so big so fast? Several theories are being explored. One suggests that in the dense environments of the early universe, black holes could accrete matter much more rapidly than they do today. Another proposes that black holes might have formed directly from the collapse of massive gas clouds, skipping the stellar phase entirely. These direct collapse black holes could start with masses of tens of thousands of solar masses, giving them a head start. There's also evidence that black hole mergers were more common in the early universe. As small galaxies collided and merged, their central black holes would eventually spiral together and merge, creating larger black holes. James Webb's observations of these early supermassive black holes are helping astronomers test these theories. By measuring the properties of distant quasars and their host galaxies, we can constrain how black holes form and grow. One particularly fascinating finding: some early galaxies appear to have black holes that are unusually massive compared to their galaxy's stellar mass. In today's universe, the black hole is typically about 0.1% the mass of the galaxy's bulge, but in some early galaxies observed by James Webb, the black hole is much larger relative to the galaxy. This suggests that in the early universe, black holes might have grown faster than their host galaxies, or that the relationship between black holes and galaxies evolved over time. Section 6. What this means for cosmology. So, what does all this mean for our understanding of the universe? First, let's be clear. James Webb's observations don't break cosmology. They don't disprove the Big Bang. They don't require us to throw out our fundamental theories. What they do is refine our understanding. They reveal details we couldn't observe before, and they highlight areas where our models need improvement. Think of it this way. Newton's laws of motion weren't wrong when Einstein came along. They were incomplete. They worked perfectly well for everyday situations, but needed refinement for extreme conditions like very high speeds or strong gravitational fields. Einstein's relativity didn't replace Newton. It encompassed Newton's laws as a special case. Similarly, James Webb's observations of the early universe are revealing complexity and detail that previous models didn't capture. This will lead to better, more complete theories of galaxy formation, star formation, and cosmic evolution. Some astronomers are revisiting assumptions about star formation efficiency in the early universe. Others are exploring how dark matter might have behaved differently in the denser early cosmos. Still others are investigating whether feedback from supermassive black holes played a larger role than previously thought. There's even discussion about whether the Hubble tension, a discrepancy in measurements of the universe's expansion rate, might be connected to our understanding of the early universe, though this remains speculative and highly debated. What's important to understand is that this is how science progresses. Anomalies and surprises don't represent failures, they represent opportunities, chances to learn something new, to discover phenomena we hadn't anticipated. James Webb was built to surprise us. It's doing exactly what it was designed to do. Section 7. What's next? James Webb is still in its early phase of operation. The telescope is expected to function for at least 20 years, possibly longer. As observations continue, we'll build up larger and more complete samples of early galaxies. Individual observations are fascinating, but it's the statistical patterns across many galaxies that will really constrain our theories. Astronomers are particularly excited about upcoming deep field observations. The telescope will stare at tiny patches of sky for hundreds of hours, capturing the faintest and most distant galaxies possible. These ultra-deep fields will probe even earlier epochs, potentially reaching back to within 200 million years of the Big Bang.
There are also plans to observe gravitational lensing clusters, massive galaxy clusters whose gravity bends and magnifies light from even more distant galaxies behind them. Nature provides a free magnification boost, allowing James Webb to see galaxies that would otherwise be too faint to detect. Spectroscopic studies will continue to be crucial. Taking spectra, splitting light into its component wavelengths, allows astronomers to determine distances, measure chemical compositions, identify star formation rates, and detect the presence of active black holes. James Webb's spectroscopic capabilities are orders of magnitude better than previous telescopes. There's also exciting potential for unexpected discoveries. Some of the most important findings in astronomy have been serendipitous, things no one was specifically looking for. With James Webb continuously observing the universe in unprecedented detail, who knows what surprises await? The early universe revealed by James Webb is not quite what we expected. It's more vibrant, more dynamic, and more complex than our models predicted. Galaxies assembled faster, stars formed more efficiently, black holes grew to enormous sizes in remarkably short times. Chemical enrichment proceeded rapidly. These aren't problems for cosmology, they're opportunities. They tell us we have more to learn, more to discover, more to understand. And that's the real story of James Webb Space Telescope. Not that it proved everything wrong, but that it showed us how much there still is to explore. The universe is under no obligation to match our predictions. It simply is what it is. Our job as humans, as curious beings looking up at the stars, is to observe, to question, and to continually refine our understanding. James Webb is giving us a clearer window into the cosmic dawn, the period when light first flooded the universe, when the first stars ignited, when galaxies began their long journey of growth and evolution, and we're only just beginning to see what's really out there. Thanks for watching. If you enjoyed this deep dive into real space science, consider subscribing for more accurate, fascinating explorations of our universe. And let me know in the comments, what aspect of James Webb's discoveries surprises you most?